you find any difficulty assessing them. Now to kickstart this day, I would like to invite Mr. T.S. Kathad, the Honorable Chair of ITA India Chapter, to set the tone for the webinar. So I request Mr. Kathad, please take over.
Thank you, Mr. Chandra, and good afternoon, all my colleagues and industry friends, and a great warm welcome to every one of you attending this online virtual webinar organized by ITA and supported by MDI. We thank you all for your taking time from your busy schedules and joining this virtual event on behalf of ITA. So, International Tube Associations is the world's largest and most influential professional membership associations across the globe for pipes and tubes industry, and offers a unique range of benefits, services, and events to promote new technology and growth within the industry. Individually, in more than 70 countries worldwide have already discovered the world of different ITA members can make to them personally and to their businesses. ITA India is based at Chennai and is involved in imparting training, helping individual professionals, organizations of its members on manufacturing and technology for the pipes and tubes. The webinar objective, the ITA chapters supported by Mr. India is holding this free webinar infrastructure for the transportation of hydrogen gas through pipelines. The webinar is intended to support the efforts being made towards the global transitions and adoptions of clean energy and achieving carbon neutrality. The free webinar will provide a bird's-eye view of the status quo and gaps towards the meeting the infrastructure requirement for the transportation of hydrogen gas through pipeline. I would like to take a few minutes where I would like to explain the hydrogen economy, which is a green energy economy in the future to come. The investment trends on the renewable energies. The renewable energies are dominating investment in new power generation capacity. Global energy investment is expected to record to 1.9 trillion in the coming years, 1922 onwards. So global energy spending expected to grow 10% to 1.9 trillion, then power sectors, then other new power generation capacities. The current investment trends remain what is required if international climate targets are to be achieved by 2050. The hydrogen infrastructures in our country, hydrogen will play a crucial role in the climate neutral economies of the futures of India, as shown in many recent scenarios and roadmaps. In a system dominated by various renewable such as solar, wind, onshore wind, offshore wind, hydrogen-linked electricities with industry heat, materials such as steel, chemical products like fertilizers, space heating, and transport fuels. Furthermore, hydrogen can be seasonally stored and transported with a cost-effective over long distances by ship or pipeline. Renewable hydrogens in combinations with the renewable electricity has the potential to entirely replace hydrocarbons in the long run, which is being used, explored for the scalability. In the short to medium terms, low carbon hydrogen is necessary to roadmap hydrogen production volumes, scale to stimulate increased hydrogen demand, support the building of a dedicated hydrogen infrastructure and development hydrogen market in our country. The year 2022 saw emergence of hydrogen strategies in many countries and regions around the world, such as UK, Australia, Japan, Korea, China, Russia, South Korea, and so on. So hydrogen has become a central element of the investment plans announced by many countries towards carbon neutrality. The global hydrogen investment pipeline surged to more than $500 billion dollars estimated as on today, has now been allocated to the investment in the hydrogen project globally over the next decades. So China is coming up with big hydrogen powerhouses and have 30% of total investment, almost 150 billions, goal to become the carbon neutral by 2060. Hydrogen could comprise of 10% of the Chinese energy mix by 2050. 53 large-scale projects have been announced publicly to date, with a 17 billion committed investment for their hydrogen economy. Europe is, as you know, the Europe and UK, they're coming up with big, investment plan and have their roadmap to generate renewable energy through wind, solar, and also offshore wind energy and hydrogen. In the US, the world's second largest emitter after China is also coming up with the roadmap, new policies for lowering their production cost and transitioning from the fossil fuel to the hydrogen. Now here we need to have a good government policy, a comprehensive and coherent policy framework is needed, supporting development of dedicated infrastructures and transparent open market. Governments need to go beyond making pledges to cut emissions and take concrete steps to accelerate investment in the market-ready clean energy solutions and promote innovations in the early stage technologies for the productions, transportations, storage, and consumption mechanism of green hydrogen in the future. Necessary resources have to be mobilized and directed to clean energy technology to put the world on track to reach net zero emissions by 2050 as per the Paris Agreement signed by various countries. Oil and gas industry showing sign of transition from fossil fuel to clean energy investment from since 2021. As you know, the government has already announced the hydrogen mission of India by our honorable Prime Ministers on 75th Independence Day to push this of the energy, as India is already importing $156 billion petroleum product across the globe to feed our to meet our consumption and demands. As already noted, renewable hydrogen productions costs around the world are dominated by electricity cost and therefore mainly determined by the renewable energy resources available. However, the production costs are not the only factors. I think that's cost factors we are going to capture in the subsequent presentations by the various speakers. The transportation storage costs have to be taken into account too. For base load hydrogen delivery to a steel plant, and the cost competitive will typically be between locally produced renewable hydrogens from solars or wind with the local storage, and limited pipeline transportations and imported hydrogen by long distance pipeline only with the safest mode. In both the cases, local hydrogen productions and import large scale multi renewable hydrogen productions will take place at the renewable production site and not at the demand side. Hence, it is important for India and all the countries to make their roadmap from today for next 2 decades. The main reason is that the hydrogen transport by pipeline is more cost effective than electricity transport by other purposes than the cables. Also, typically the pipeline capacities are much larger than the electricity cables, whereas it goes from 15 to 20 gigawatt to 1 to 4 gigawatt. So I'm sure all of you participants will gain the knowledge on the hydrogen infrastructures, what is needed for the next decade. And it is important for us, all of us, to make sure that we gain more knowledge on the material technology, the productions of hydrogen, green hydrogen gases, and there are various organizations pushing the renewable energy in the future to come. And I'm sure the speakers, what we have selected, all the executive members of the ITA, you will see the variety of papers from the oil and gas, from steels, from the industry experts, those who are already working in various aspects of hydrogen's infrastructures. Now, as the tone for the webinar is already set, without any further delay, I would request Mr. Chandel, who is our moderator on behalf of ITA, to take the proceeding further. Thank you very much, and hope you will see a great learning.
Thank you, sir. Thank you your deep insight for the future of this hydrogen fuel. So let us start today's event. The first speaker is Mr. Kowtham Raj. He's the Director, India Energy Storage Alliance and Customized Energy Solution India. The topic is Green Hydrogen Ambition of India. So, Mr. Raj, I'm just sharing your presentation.
Sure, sir.
Please start.
Okay, sir. So if you could make it full screen, slideshow mode.
Mr. Raj.
So can you hear me?
Yeah, yes.
If you could make it full screen, it would be better, I think.
Okay.
Thank you.
It's a full screen now.
Yeah. Thank you so much, sir. Thank you so much for ITA for inviting me to start this very exciting but also very important discussion. So I'm the director of IESA and also CS India for new initiatives. But before CES, I was part of NITI Aayog's team, where I written the first policy paper on green hydrogen in India, along with multiple colleagues from multiple industries. So we are very, very excited about green hydrogen, and we strongly believe India can be one of the leaders in the world when it comes to green hydrogen. Next slide, please. So among multiple technologies, energy storage as a technology, as a platform technology supporting multiple sectors, has took off since early 2000s. It is, especially in batteries, the lithium-ion batteries have taken off like anything, and it has become one of the largest industries in the world. Chinese richest person is owner of a lithium-ion battery company called as CATL. So the energy storage technologies and the new and emerging energy technologies has transformed from a niche technologies to a mainstream technology. And just like batteries have helped the development of multiple allied ancillary industries in electrical connections and so on and so forth, hydrogen industry, especially green hydrogen industry, if it goes through the same kind of growth pathway that batteries have taken in last 10 years, we do strongly believe that hydrogen would follow the battery's path, albeit in a different kind of applications, which I would come later on. But there's a significant potential for a lot of ancillary industries to benefit from this ecosystem. And one of the biggest ancillary industries in this green hydrogen movement would be the pipes and tubes industry. Next slide, please. So one of the reasons why India is looking at green hydrogen is very important to understand that India imports almost $150 billion worth of energy every year. And the International Energy Agency, NITI Aayog, and everyone else, every reputed agency in the world predicts that Indian energy demand would double in the next 15 years. If Indian energy demand would double in the next 15 years, our energy import demand in a BAU scenario, in a business as usual scenario, it would also double and it become $300 billion. When India's energy import is $300 billion, what happens to our foreign exchange? Our currency would strengthen, would weaken. So it has significant energy security and economic security issues. So we cannot continue this path. That's exactly why in August 15th, Honorable Prime Minister of India announced and reiterated the importance of green hydrogen for India, and especially in reducing imports and reducing emissions. And he actually pledged that he would really like to make India an non-energy importing country, that zero energy importing country by 100 years of independence or thereabouts. So to meet this ambition, which has multiplier effects across our economy, green hydrogen would play an important role because green hydrogen is local energy source. Next slide, please. So another thing to understand is only 17% of India's total energy consumption is in form of electricity. When we talk about energy, the conversation always revolves around electricity. But 83% of our energy in terms of oil, coal, gas, all of them are imported in significant quantities. And this imports would only go up. But not all of these imports could be replaced by hydrogen. No, hydrogen is not the right technology for all the energy applications, but for certain energy applications, especially hard to abate where sectors where you cannot electrify, that is where green hydrogen plays an important role, and that itself is a huge, enormous sectors with enormous demands, with multi-$100 billion and multi-trillion-dollar global value. So green hydrogen has an enough market to play in this hard to electrify or hard to decarbonize sectors. Next slide, please. So there are two kinds of, many of the audience would probably already know, but for someone who doesn't know, are not aware of the different types of hydrogen applications, there are two kinds of hydrogen applications. One is feedstock and another one is energy. And feedstock is the largest application now. It's going to be the largest application for at least next 10-15 years. And energy applications would take over from feedstock applications maybe in 15-20 years. But as of now, in the immediate term, the biggest demand is going to come from feedstock sectors like refining. In refining is nothing but purifying or value adding the crude oil. So to remove the sulfur and also to saturate the products of crude oil, we need hydrogen. And as more and more stricter regulations are coming for gasoline, petrol, and diesel, the hydrogen demand in refining would continue to go up. And in fertilizers, 80% of urea is actually hydrogen. So even in new kinds of fertilizers, hydrogen is required. The fertilizer is the largest demand sector for India, but refining and fertilizers are the two largest sectors in the world. And steel is a sector that are one particular kind of technology, which probably all of you know, DRI technology uses hydrogen. But we do believe that in the future, steel is going to be probably the biggest hydrogen consuming sector in the world, even beyond transport and any other applications. And methanol and chemicals are a few other applications. Energy, the biggest immediate demand for hydrogen could come from blending with natural gas. So natural gas is nothing but methane, and methane, as you know, like has much higher greenhouse gas potential, greenhouse gas emissions potential. It affects the climate change worse than carbon dioxide. Some experts do say that. So we need to avoid as much as possible import of natural gas to do that, but we need gas for many of our applications. But the ideal solution could be blending a little bit of hydrogen with natural gas. But again, that's where the tubes and pipes industry has a major role to play to make sure that India's gas pipelines are ready, are hydrogen ready for the future. And the next applications we see is the heavy duty for light applications for cars, two-wheelers, three-wheelers, or light trucks. We don't see hydrogen being competitive with batteries that are appropriate for these applications. But for heavy duty, long distance applications, for marine applications, for heavy and long aviation applications, definitely hydrogen is a very attractive option, especially for marine applications. International Maritime Organization has said by 2025 they want to really decarbonize their marine transport, and it's an economic imperative as well. Everybody is worried about carbon intensity of their products. When Apple iPhone is shipping chargers or components or cases from China, it doesn't want that ships to have very high carbon intensity, because that would add to the carbon intensity of iPhones the consumers across Europe would buy. So because of that, marine is one another very attractive application. And in the very distant future, in countries like Europe, where there is seasonal demand for energy storage, definitely hydrogen could play a role. Next slide, please. So of course, everybody knows there are multiple different types of hydrogen, and many countries are pursuing different kinds of hydrogen depending on their own natural resources. But India's natural resource is nothing but solar and wind. Because of that, we have coal, but we import 200 million tons of coal. The coal as a percentage of our economy goes up, goes down, but absolute demand for coal keeps going up. But we are not able to satisfy our own coal demand. Because of that, we are importing 200 million tons of coal and 50 million tons of coking coal. Because of that, green hydrogen, India, even the Honorable Finance Minister in her budget speech announced that India would focus on green hydrogen mission exclusively from renewable power sources. So, unlike many other countries who are confused between different kinds of hydrogen, India is only seeing one color, and it's green. And that's how the all the government indication shows. Next slide, please. Of course, as I told you before, there are multiple different sectors of hydrogen, but big hydrogen consumers are in the feedstock. New use cases are gas. Future we see energy applications. Next slide, please, sir. Next slide, sir. So the current demand of India is not a small country when it comes to hydrogen demand. India is already one of the largest consumers of hydrogen in refining and ammonia sectors. And one another thing is India almost consumes 10% of global demand. In addition to that, India's demand is for hydrogen without any government support, just because of expansions in refining and fertilizers, is going to double. Because our current refining capacity in the country is 249 million tons, and India is going to expand to 440 million tons of refining by 2030. And with higher and tougher sulfur regulations, more hydrogen would be required to create high quality petrol and diesel. And a lot of studies have done. Terry, for example, done a study, and we also have done multiple studies. We see that without any interventions by 2030, green hydrogen cost would probably come to $2 per kilogram. Multiple people have multiple different opinions on it. There's no one number, but ideally speaking, the government of India and industry, ideally the plan is to bring, the aspirational plan is to, can we reach that $2 by 2025, by 2026? If that happens, that at $2, the gray hydrogen and green hydrogen becomes it reaches parity, and the demand can scale up quickly. And whenever this $2 is reached, the demand, multiple demand sectors would go up. But by 2050, people see that green steel is going to be the largest demand sector among industrial features. Green steel is going to be the largest demand sector for green hydrogen to make steel. Next slide, please. And we do see that some of our analysis says that by 2050, in a conservative scenario, depending on technological evolutions, hydrogen could see 5 to 10 times increase in demand. And of course, this would also increase significantly the demand for pipes. And depending on the modalities of hydrogen production and consumption, it could also increase the demand for the pipelines, which are hydrogen ready. And almost 26% of emissions could be reduced just by green hydrogen. And steel and heavy duty trucking will be the largest demand sectors by 2050. But in the near term, refinery, ammonia, gas blending are potentially the largest sectors. Next slide, please. So IESA as an industry collective and a think tank, we started this initiative in 2020, mobility and infrastructure with green hydrogen technology. It's across all green hydrogen technologies and across all green hydrogen applications. IESA works to support them and works with multiple 150 other associations across the world to develop this technology and promote this technology and promote the development of these technologies. And similarly, collaboration with the pipes, tubes, and steel and associated industries would really help in bridging together the knowledge we have. These two industries should come together to make this happen. Next slide, please. So public announcements by the government as green hydrogen mission document was under works by the MNRE, but they are continuing to revise it. And multiple times the power minister has announced that green hydrogen purchase obligations for refining and fertilizer sector is supported, and we do believe this is the best way to scale up hydrogen. And potentially in the near future, depending on the technical data and technical pilots, even blending for gas is something which we may want to promote and support. And there was also announcements and news about green hydrogen or ammonia tender by central agency like SECI. And there is also an announcement about potential production linked incentives for electrolyzers, because there's not enough electrolyzers in the world. So if you don't have enough electrolyzers, then we really cannot make green hydrogen. So India might be one of the largest manufacturers of electrolyzers if right things are done. Next slide, please. Next slide, please, sir. Next slide. The next slide, sir, please. Yes. So we see like the three kinds of opportunities are possible. One is the electrolyzer OEMs, electrolyzer components. The third kind of opportunity is relevant to this audience, are the EPC pipes, operation and maintenance. An enormous amount of pipes. Even if hydrogen is produced on site, still a significant amount of pipes would be required to circulate to circulate water, oxygen, wastewater within an electrolysis system, and taking those hydrogen and putting it inside and demand sector like refining and fertilizers where pipes are involved. And once a significant amount of demand is created and scales are generated, and potentially in a long term or a medium term, even pipelines, hydrogen ready pipelines. For example, in Germany, there's a project where there's a centralized hydrogen, large electrolyzers produces large quantities of hydrogen, and through pipelines within a short radius, but multiple chemical industries are getting green hydrogen using these pipelines. Such things might happen once enough demand is created. Next slide, please, sir. So another thing is like steel. As I said, steel is one of the largest demand sectors. Again, there's a lot of potential for tubes and pipes and several other associated technologies. But we do see that there's multiple technologies competing with each other. Biomass-based technologies are there. Multiple disruptive electrolysis-based technologies are there. But we do believe that direct reduction of hydrogen combined with electric arc furnace could be the potential winner. If that happens, then steel would require a large quantities of hydrogen, and that would also generate a lot of demand for pipes and tube sector. Next slide, please. So we also believe, because we have relatively cheaper hydrogen prices and appropriate cost advantages, in the near term, India could be one of the best locations to make green steel. And unlike all the other technologies, we wait for the world to move to a new technology and then we move. But if it's possible, if the government and the industry can work together to make probably India one of the first countries to move towards at least a small portion of their new capacities into green steel. I think there are people who are willing to pay more for green steel, and when they want to pay more, and the India-based green steel might be the cheapest green steel across all the countries. And our analysis do say that, and this is a conservative analysis. And if Indian green hydrogen reaches $2 or $1.5, it could be very attractive opportunity for manufacturing and exporting green steel from India. Again, that would create a lot of opportunities for this sector. Next slide, please. So this is my last slide. I would like to stop here. And we do believe that India is very well placed to capture green hydrogen technology opportunities. The growing market, not many competition like in other solar or other sectors, very significant Chinese competition. And there's a strong potential for manufacturing cost reduction, both in the pipelines, electrolyzers, components, everywhere, because no one has taken a leadership yet. We can be one of the largest producers of hydrogen-ready pipes, hydrogen-ready pipelines, green hydrogen electrolyzers, green fuel cells, etc. So we need to build our demand and manufacturing hand in hand. And we are also strategically located close to APAC countries like Singapore, Taiwan, Japan, Korea, who wants hydrogen, who depend on hydrogen to decarbonize their economy, but they don't have renewables, they don't have cheap labor, and they don't have project execution capabilities that we have in green technologies like solar and wind. So there's a strong potential for India to export green hydrogen carriers like ammonia or methanol to these countries, potentially, if things are done rightly, and high degree of localization is possible. So we do believe that India is well placed to capture the green hydrogen tech opportunities, and we want the pipeline industry, industries to be ready. Thank you for inviting me. Thank you for giving me the time.
Thank you, Mr. Raj, for your elaborative explanation on the vision of India's hydrogen mission for future. And we can be leader in hydrogen production and usage of hydrogen. Thank you very much.
Thank you, sir.
So next topic is cost reduction of large renewable energy hydrogen projects by Mr. Jay Chaudhary, Senior Energy Industry Executive with International Project Delivery track record for upstream and midstream projects, North Sea, North Africa, Mediterranean, and the Black Sea. He worked with companies like Aramco, specialist in offshore renewable energy energy infrastructure design for wind power, hydrogen projects, and oil and gas development involving deep water, subsea, and pipeline technology. He contributed many papers in the international journals and various conferences to enhance the knowledge of the people across the globe. So, Mr. Chaudhary, we welcome you, and just sharing your presentation. You can start, please.
Okay, thank you, Dr. Charnel. If you could put up the slides, please.
Yeah, just put it.
Hello, good afternoon, good evening to everybody who's listening. If you could make it full screen.
Okay, I'm doing it.
Welcome, Mr. Jay.
Okay. Yep. So, yep. In continuation of the previous speaker's speech, it's very, appropriate that my slides actually renew the theme and confirm the theme which he has expressed. And the topic is large renewable energy hydrogen projects. In essence, these are green hydrogen projects and how they can be made economic to the advantage of everybody, particularly those sectors which are hard to abate, as the previous speaker have said. Next slide, please. So I'll capture the theme in 5 specific areas. Is the renewable sustainable industrial fuel, should it be hydrogen or should it be something else? At the moment, answer is yes, hydrogen is the prominent competitor there. How to get there? How to decide how to mark out the pathway so that we can produce green hydrogen at scale? Because you can see the challenge for the climate issues to get to 1.5 degree, to retain 1.5 degree rise, we need to have green hydrogen at scale. Otherwise, we are not going to achieve it. The next topic I'll discuss are what are the immediate cost and technology challenges for large-scale electrolyzer installations, how to get that hydrogen into the market which is crying out for green hydrogen. And in order to make sure the cost of green hydrogen does not exceed the current prices these industries are using based on fossil fuels, we have to bed in the cost reduction. Again, the previous speaker indicated $1 per kilogram of hydrogen is an ideal price range, long-term price range. Okay, next slide, please. So, as already said, several industrial economies have already taken their targets seriously and published roadmap how to make sure that they can produce hydrogen in bulk quantities to meet their carbon emission targets in order to satisfy their domestic industrial power and transport sectors. So again, hydrogen could become a very important industrial feedstock, again, which has been confirmed by the previous speaker. Transport, heavy duty transport, including marine transport, power generation, and to some extent where it can be done for block heating, combined heat and power. Domestic heating is an example where large blocks of commercial and domestic properties can use hydrogen as a direct replacement of fossil fuels. Green hydrogen will depend in renewable solar and wind electrical power in a large way to make sure that the cost of green hydrogen could be at par with the industry's needs. And places like India, Australia, most of North Africa are blessed in this area because of their climatic advantage. Currently, the gap which green hydrogen cannot meet is likely to be filled by blue hydrogen, which is why most of the industrial economies are banking on blue hydrogen as a stepping stone in order to meet their green hydrogen targets in 20 to 30 years' time. Currently, green hydrogen has a price disadvantage to blue hydrogen. Blue hydrogen is comparatively better priced at the moment, not as cheap as gray hydrogen, but the gray hydrogen means carbon dioxide is emitted to the atmosphere, whereas for blue hydrogen, carbon would be captured and sequestered in ground. But that price disadvantage can be overcome. And the main ingredients of price disadvantage are renewable electricity price, electrolyzer material technology, the relative size of the plant operating cost, and I'll capture all of those in more detail later. Now, as I kept on referring, both for domestic, whether you're a trucking company or whether you're a steel making, the green hydrogen has to be as competitive to the nearest competitive fuel to make sure the acceptance is done and that we can transport it safely to the customer. Next slide, please. Right. Now, we're talking about gigawatt size green hydrogen plant. In order to get there, let's capture what has been done so far. In 2019, Europe started off the first sort of green hydrogen plant at 5 megawatt, shortly followed by Shell's Rhineland refinery in 2021, which is earlier this year, which amounts to 1,300 tons of hydrogen per year. In fact, that particular refinery uses every year 13,000 tons. 13,000 tons. So the 10 megawatt only produces 1/10 of the factory's needs. Okay. Now, in addition, industry has now convinced that there's capacity in the market to produce electrolyzers and renewable power. Most of the European renewable power is being fed to home and to the industry. To make room for in the green hydrogen, they have to be positioned in a way there's plentiful wind power there to make sure that can be captured. So at least 320 megawatt per green hydrogen schemes are approved, but quite a few schemes are in different stages of planning, which are ranging between 40 to 200 megawatt. But most of you have heard that Saudi Arabia is planning the first gigascale green hydrogen project at the NEOM city. They plan to produce 4 gigawatt of renewable electricity to produce 650 tons of hydrogen per day. And in order to feed to the ammonia plant, which they're going to look at. Most of that ammonia would be transported to Europe, where they could be converted into either fertilizer or converted back into hydrogen. In addition to NEOM, Oman has recently signed a memorandum of understanding with an Indian company called Acme Solar to install a 3.5 gigawatt green hydrogen plant at the Duqm port. In addition, Endesa is also looking at 650 megawatt solar plant in Portugal to produce hydrogen for local industrial consumption. So all of these are good omen that green hydrogen plants are being developed, are being implemented. Next slide, please. Okay. Now we're getting down into more into nitty-gritties. What are the main challenges? Alkaline and PEM, proton electron electrolyzers, are the most common, but PEM electrolyzers are still far too expensive compared to alkaline. Though PEM electrolyzers have other efficiency aspects, then that's why Shell has used PEM electrolyzers for their Rhineland refinery. In addition, new competitors are coming in. Previously, what used to be called solid oxide fuel cells, they are also producing solid oxide electrolyzer cells. They have low electrode costs compared to PEM. PEM uses more expensive platinum, iridium electrodes. Currently, electrolyzer stacks need to be replaced every 7 years. Alkaline electrolyzers do need very high quality water. So there are a lot of issues which control the efficiency of these electrolyzer plants. In order to ensure that this could be resolved and the economies of scale as well as the efficiency of those installations could be improved, there's a lot of research and development going on. In parallel, most of these small scale electrolyzers, when I say small scale, up to 10 megawatt, 20 megawatt installations, are using manual and specific industrial labor to produce it. Automation is coming in a big way. Good news is that UK's ITA Power has already put a gigafactory which will be producing electrolyzer stacks with a maximum amount of robotization and automation. NEL in Norway and across the world has also setting up more automated plants, just like the Elon Musk's battery factories are being automated to a large extent. Automation is expected to have a big impact in terms of making sure electrolyzers remain competitive. But the biggest impact on green hydrogen is the cost of renewable power. The subsequent slides would show that. And if all of these previous issues could be resolved to the industry's advantage, green hydrogen can drop in price by nearly 80% within 2 decades. That's the good sign that green hydrogen can be made a reality. Next slide, please. Next slide. Yeah. So I won't spend too much time on this. This is based on analysis done by Industry Association, IRENA, which shows where the most impacts are. Power supply, bipolar plates are the most important issues for PEM electrolyzers. Other ones have a relatively less impact on it. If you compare to that with next slide for the alkaline electrolyzers, power supply remains at the very high point. So overall, if you deal with power supply, you deal with manufacturing, and you do deal with a couple of the other issues, you do get a big price impact on the manufactured cell price from these electrolyzer companies. Next slide, please. Now, if we can produce hydrogen at a competitive price, they have to get to the market, because plentiful, take Indian context, plentiful sun in a non-urban setting is in Gujarat, in Thar Desert, in Rajasthan areas where population densities are less. If you want to site a massive solar plant combined with wind energy plants, you need to be close to the shoreline in order to make sure that you have access to desalting the seawater and use that as a feed water for electrolyzers. If you do all of that and get your input prices right for green hydrogen, it still has to go to the industry where they are located. Industry is not going to come to next door to the energy supplier. They have to be transported. Pipelines remain the most effective means for that. Ship-based hydrogen transport are being considered by countries like Australia, Saudi Arabia, Oman, to export to Japan, Europe, USA, etc. A recent study has shown the cost of transporting hydrogen would be around 0.11 euro to 0.21 euro per kilogram per 1,000 meter. That's by pipeline. The charts on the following pages would show. So currently, previous speaker mentioned repurposing existing pipelines is a good way of kickstarting the hydrogen economy. And in that sense, Europe has already taken steps. They have got aggressive targets. They want to repurpose existing pipeline, build new pipeline to the tune of around 11,600 kilometers in the next 9 years. And again, nearly have 3.5 times to 4 times more by the year 2040. So a fairly aggressive target. All of these are captured in the European Hydrogen Backbone Study. Next slide, please. Right, so the comparison here is between, liquid hydrogen, that's the sort of a deep blue line, that's with ship, and this is organic hydrogen carrier. Hydrogen has been dissolved into an organic compound, which can then be easily transported. And then this line is for ammonia. Rest are pipelines. And you can see how easy pipeline, in terms of economy of scale, that up to 6,000 kilometer transport distance, repurposed pipelines are the most effective means of transporting hydrogen. Next slide. Right. So this again, ship-based transport versus pipeline transport. You can imagine what the costs are. Pipeline is coming here, but this pipeline has to cross several frontiers. Saudi Arabia to Turkey, Turkey to Greece, to get to the market, wherever the European market is. So developing these sort of projects are multi-country pipeline transport is a very big challenging job. Compared to that, that means any Saudi Arabian production would be remain locked up in this price band in terms of transport. Okay, next slide, please. So what are the potentials for, I've touched briefly on that. The industrialization arena has captured the 6 key areas. And first one is electrolyzer design constructions. The new designs which are coming in, they are being made, each individual electrolyzers are 5 megawatt unit, and they are combining into 20 megawatt, 20 such units to make a 100 megawatt installation. Very modular. As a result, balance of plants, the piping, the storage, all the pumping, electricity supply is then basically generated for each 5 megawatt. That way, if they need to maintain one part of the plant, say 100 megawatt or 200 megawatt plant, they don't need to switch off everything. So there's a lot of modularity coming in. Economies of scale, where the mega factories are being designed and built with automation, the cost savings are of the order of 50% immediately. Sorry, previous slide. Yeah, and then it goes on, material procurement, which PEM electrolyzers are at the moment most in demand, but they have iridium, platinum, rare metal issues, whereas alkaline, SOEC, and AEM electrolyzers do not use that type of rare earth material. I mentioned modular design of stack and balance of plant issues and the storage of hydrogen. There's a big impact there. quite a lot of industries are basically deciding to install small off-grid installation at truck bus depots, at big locomotive depots, to make sure their local needs are met and they don't need transport by pipeline at peak times. And another issue is, as experienced with solar cells, initial design to actual performance showed nearly 50% improved in the learning rate. That means as industry uses more and more of the same component, the efficiency of the installations and the design of the installations becomes better. And we expect similar improvement also come from the electrolyzers. Next slide. So this confirms again the previous authors, previous presenters' assumptions that it is possible to move the price of hydrogen from around $5 per kg to $1 per kg. So this is a possible future. In order to get there, the intermediate steps are outlined here. Again, this is based on an industry analysis. They have surveyed a number of electrolyzer manufacturers and how to get there. Next slide, please. It's quite dense, but we need to move from this band to that band. And if we can achieve all the previous targets in terms of how to get to the economy of scale, how to reduce the cost of electricity, I think there's a good possibility that we will get that. Anybody who wants to review that in detail can look at the IRENA report. Next slide, please. Okay, so I'm coming to the end. So cost reduction for both CapEx and OpEx for large green hydrogen plants are quite feasible, but the main ingredients, the renewable power cost has to come down, and the electrolyzer stack cost has to come down. Without that, the chance of reaching the $2 goal or $1 goal per kilogram of hydrogen would be remote. The fact that the industry is getting a big push by outfit like NEOM, by Oman, as well as the number of companies in Europe who are already pushing ahead with 200 megawatt, 100 megawatt hydrogen plants. For India, it plays a big role because abundance of solar energy and the proximity to the coastal area for desalination of seawater if needed, if the domestic water supply is not sufficient enough. A number of automated plants are being set up to take care of this gigascale capability for producing electrolyzers. Two companies, ITM Power and NEL, has already taken steps in that area, put funds in place to make it happen. And the last bullet is that in order to deliver green hydrogen, the best choice for India is to use pipelines, either repurposed or brand new, to take green hydrogen from places like Gujarat, Rajasthan. And I'm sure some other states would also find that they can release enough space, enough facilities to set up local solar farms and set up hydrogen to meet their industry needs. In terms of operating experience with hydrogen pipelines, some of you already know the statistics. Hydrogen pipelines do operate in Europe and also in USA. So hydrogen can be operated in a safe manner. It's used in plentiful in ammonia plants and also in refineries. So there's a lot of industry knowledge. So concern about hydrogen safety should not be overplayed. Thank you. Thank you for listening to me.
Okay, thank you, Mr. Chaudhary, for your elaboration on cost reduction of large renewable energy hydrogen projects and various sources of hydrogen and their cost comparison with respect to the source. So I think the audience will get definitely benefited from this informative presentation. Thank you very much.
You're welcome.
So next speaker is Mr.Alok Gotru. The topic is pipeline integrity, operation and management for hydrogen and natural gas. He has worked in responsible senior position in project construction, operations, maintenance, and pipeline integrity management. The companies like Tata Steel, GAIL India, RGTL, and RGPL Reliance Group. Is presently working as a full-time director. Reliance Ethane Pipeline Limited is also heading Center for Excellence of Pipeline for all NG and petroleum pipelines in Reliance Group companies. He has presented several technical papers at international conferences in India and abroad. So I welcome Mr. Gotru, and as I understood that Mr. Gotru will Mr. Alok Gotru will share his presentation his own.
Yeah, thank you, Dr. Jagdev. Can you please enable that? Can I do it?
I can do that. If you are facing any problem, please.
No, I have made little changes. So if you can, enable it so that I can use it from my side.
Okay, okay, we are doing that.
Presently, it is disabled.
Yes, sir, we have enabled it. You can,
Okay.
you can share it.
Yeah, are you able to see it and hear me? There is some internet problem, so there is some interruption in between. Are you able to hear me?
Yes, yes.
Yes, we can.
Okay, thank you. So, good afternoon to all of you.
afternoon, sir.
Distinguished guests, speakers, delegates, ladies and gentlemen, welcome to my presentation on the proactive approach towards maintaining asset health, particularly in context to the pipeline assets, on which I would be talking about today. At the outset, let me thank the organizers, ITA India chapter, for giving me an opportunity to speak at this webinar on a very important subject on hydrogen transportation through pipelines. Though the webinar is on hydrogen transportation, the previous presenters, they have covered various aspects of the marketing, the cost part, the various sources from where we can get the hydrogen. I would be covering basically on the integrity aspects of the pipeline. That means on the proactive approach towards maintenance of all type of assets, particularly focusing on the pipelines, which is the topic for discussion today. I would be centering my discussions around the famous proverb, a stitch in time saves nine. This is a very famous proverb, so I would be centering around this philosophy. This proverb is applicable and relevant for maintaining health of all type of assets, which is so important to run any business. Pipelines, you all know, they are the arteries to supply the product or the energy to all vital operations. It cannot be ignored or overlooked. Maintaining health and integrity of the pipelines is therefore very, very important, because these pipelines, they pass through highly populated and industrial areas, and any failure could be extremely disastrous. When it comes to transportation of a highly flammable and diffusible gas like hydrogen, it even becomes more necessary and challenging too. Now, I would be covering in short what are the different type of assets which are essential to be maintained for any entity to survive. The pipeline, of course, it is a unique asset, different from those of the plants or the other type of assets, which are the risk involved in pipeline transportation. The traditional approach, how the pipelines have been maintained in the past, how the integrity has been managed in the past, and what is the current practice through the integrity management system. Then the focusing on the preventive and predictive maintenance techniques, typical the maintenance and repair activities on the pipelines, and of course, the conclusion. So you will all agree that the workforce who handle and operate the physical assets need always to be fit and healthy. Otherwise, how they would be able to operate and maintain the critical assets of the plants or the pipelines. So we should give maximum attention to the health of our employees. In the present pandemic, we have seen how the companies have taken proactive measures to ensure that all their people, all their employees are vaccinated so that the work does not suffer. Then you may be also aware that for any cross-country pipeline project, we have to take various environmental and forest permissions from the government agencies, like the pollution control boards, the Ministry of Environment, Forest, and Climate Change. This is, of course, necessary for sustaining life on this planet, then giving a good and clean environment to the society. So maintaining environment is also an important aspect of any integrity management system. Now, the financial health, without a sound financial health, no entity or even any country can afford to create a network of pipelines and thereafter maintain its health. As we know very well that pipelines are very highly capital intensive projects, and therefore the financial health of the entity has to be very sound in order to sustain the pipeline operations or in fact any business. The intellectual assets, in our quest to maintain these physical assets, we often tend to lose focus on our employees, who basically are the brain behind to operate and maintain these physical assets. High attrition rate in any organization could be an area of concern and could result in compromising safety and integrity of the physical assets. Now, the pipeline, now coming back on the subject of maintaining the integrity of the pipeline assets, which can broadly be classified into the rotary, static, and the others, where you will find that typical compressor stations or the pump stations, which basically compress the fluids in order to maintain the flow, the pipeline itself and the various valves, filters, etc., which are en route installed on the pipeline, they are also important. So we see that they are the typical assets which basically the health of which have to be maintained in order to keep these assets always fit for purpose. Now, for people who have worked in the operation and maintenance of pipelines are well aware that this is quite different from the assets of any other plant. So you can see that most of the pipeline, the cross-country part, is buried deep underground, not visible to the people. They pass through all difficult terrains like the water bodies, the forest, and most important, they are vulnerable to third-party damage, which is one of the greatest threats to the pipeline integrity. It contains a huge stored amount of energy, especially for gases. And in case of rupture or leak, we have seen how disastrous it could be. Now the incidents or the accidents can happen anywhere in the pipelines. It can happen in plants. It can happen anywhere, maybe in air, road, water. But we have seen that basically for pipelines, it is a little different as compared to the plants, because the pipelines, they pass through, very remote areas, very highly populated areas. There are no facilities available to control the fire or the disaster. So we have to depend maybe on the government agencies, or maybe sharing the resources from the other organizations. Whereas in a plant, we have the facilities available. So in case of any incident, it can be easily controlled. So this is how, it is a challenge, especially to face the emergencies in the pipelines. This slide depicts the complete risk profile, right from the identification of all hazards associated with the pipeline, which we refer to as the hazard study. So that starts with the hazard study, where all the hazards, fire, explosion, or terrorism, pandemic, whatever the hazards could be possible. So we identify what could be the hazards which could be involved. Once the hazards, they are identified, we go for vulnerability study for each of these hazards. I mean, who all are vulnerable, maybe the people, property, or the environment, which could be vulnerable in case, especially for the pipelines. And finally, the impact analysis can quantify the complete losses resulting out of any untoward incident. It could be tangible or it could be intangible. And the most important amongst all is basically the loss in reputation of the company, which could take years to build up. So here, the companies have to safeguard. For the people who have been involved in design, construction, operation, and maintenance of pipelines way back, maybe in the 80s, 70s, or 80s, for people like us who have worked during those times, we know very well how much importance was given to the pipelines at that time. That was a philosophy that just build, bury, and forget. And this used to happen. And there used to be frequent breakdowns, leaks. People used to put the clamps on the pipelines and then move ahead. And there was some acceptance to the leak at that time, though now all the companies, they have almost zero leak target, KPI is a zero leak. So this is, the traditional approach. And now, as you see, that there has been a constant pressure from the public and the government, which has made the regulators also pressing the companies to have a robust integrity management program. We know that any incident, however small it is, it has the potential to cause a lot of damage in terms of money and damage to the environment and even loss of valuable lives. We have seen in the recent times some of the accidents of pipeline in India and how the public outcry has been there. Besides a lot of pressure from the government agencies to immediately suspend operations. This always happens. This could severely impact the business and could create negative perception in the society, which could take years and years to overcome. As we are stepping in the business of hydrogen transportation through pipelines in India, we have to be very careful and conservative in designing the high-pressure cross-country pipeline systems, as the product hydrogen is somewhat unique and even more hazardous with respect to the normal petroleum products which we transport through the pipelines. Now, this is basically a typical approach to the pipeline integrity management system. We call it PIMS. I need not to amplify the importance of this integrity management system, as it is not only essential for the safety and reliability of the pipeline operations, but it is now a mandatory requirement from the statutory and regulatory bodies, especially the PNGRB, which is now in existence. The process of the flow chart of PIMS, you can see here, this is based on B31.8S. Now, this is basically for the natural gas and the petroleum pipelines. For hydrogen pipelines, I believe the integrity management plan and the emergency response plan would be a little more stringent as compared to the natural gas due to more hazardous characteristics of hydrogen. So it is yet to be, I think there's no regulations as on date. So as and when these pipelines will come in India, there would be basically a separate integrity management plan, though the basics would remain the same, but the nitty-gritties of the integrity management, the mitigation measures and all that would be a little different as compared to the petroleum products. Now, notwithstanding of all that I have spoken so far, what is basically the essence of my talk? I have basically centered my discussions on the stitch in time saves 9, meaning thereby that the maintenance or the inspection done well advanced has enormous potential to save the precious resources, which otherwise would have spent many, many times more in the repair of that pipelines. So a proactive approach focusing on the preventive and predictive maintenance is the right choice, particularly for the pipelines where the stakes are very high and no operator would like to risk business or loss in reputation. Another famous saying that fits in very appropriately for the pipeline transportation is the prevention better than cure. You can see here what is the importance of the timely intervention. As you all know that pipelines, the repair and maintenance of the pipeline is quite expensive. It is capital intensive. Even laying is capital intensive, and later on maintenance also. For example, if it is if it is a main line, then you would be requiring the hot tapping and stopping operations for doing the maintenance. So you can see that how the failure rate as the pipelines grow older and older, and most of our pipelines, petroleum pipelines in India, are beyond their design life. Even the HBJ pipeline, which was laid by GAIL way back in the 1987, now it has crossed the design, and many more pipelines belonging to Indian Oil or maybe Oil India. They are now quite old, and the failure rate increases with time. And if you don't maintain it, if there's a lack of maintenance, then it could increase exponentially and would lead to sudden collapse or failure, which is not desirable and which could be very, very disastrous. So we have to be very careful and always try to be proactive and rely on the preventive maintenance techniques like the intelligent pigging or the smart pigging, we call it, so that we know in advance what are the defects in the pipeline and we can take mitigation measures. The typical maintenance and repair activities pipelines are somewhat a little different from those of the plants where, you know, a lot of emphasis or a lot of focus is there on the various surveys, because the pipeline is spread all over in long distances and in beyond the geographical boundaries of the plants. A lot of surveys like the aerial surveys, line walks, CP surveys, all these are required as a part of the integrity management plan to ensure that the pipeline is always fit for purpose. Otherwise, you know, somebody would tap the pipeline, somebody would damage the pipeline, which could result in serious consequences. The repair part also is a little different, maybe from the conventional repair techniques. We use specialized equipment like the hot tapping and the stoppling, where we make the repairs or on the pipeline while it is in operation and can prevent huge loss in production losses. Now to conclude, I would like to emphasize again that the proactive approach towards the maintenance of all type of assets is not only imperative to run the operations safely, but also to sustain the business in the long run. Now, out of all the assets we have discussed, I would urge the industry to pay utmost importance to retaining the skilled and competent manpower, without which it would be difficult to run the pipeline operations or any other, in fact, any other critical operations which require special skills. Now, this is the problem which the pipeline industry or the some of the oil and gas industries is facing. A high attrition rate. There are no experienced people available for the pipelines. So people, the companies are facing a lot of issues of attrition as on date. The pipeline density in our countries is still very low as compared to the developed countries. And so the future of pipeline appears to be very promising. I would once again urge the audience to always remember the famous two sayings, penny wise, pound foolish, which we should always avoid, because there's always a tendency to save some amount of money, and later on it ends up in spending almost double or triple the amount which we have saved. So it is always better to be penny wise and pound foolish. Should never follow that. And we should always try to follow the proverb, the stitch in time saves 9, because this is the mantra for the sense of the pipeline integrity, sound pipeline integrity management system, which focuses more on the preventive maintenance techniques. I'm sure that if we follow the proactive approach, this would not only result in safe and uninterrupted operations, but would also enhance the life of the pipeline assets beyond the design life of, say, 25 to 30 years. So with this, I end up my presentation. Thank you, all of you, and wish you a very happy learning ahead. Thank you.
Sir, you are on mute.
No, I'm not able to hear.
Sir, thank you very much for your very informative presentation. The delegate definitely will get benefited out of it. Thank you very much.
Thank you.
So next speaker is Dr. Saurabh Kundu. And he is Chief Process Research R&D Division in Tata Steel. His area of interest. Mr.Alok, kindly please unshare your presentation.
Yeah, I'm trying to remove it.
Renewable test production of green hydrogen, carbon dioxide mitigation, iron and coke making process, alloy design, thermomechanical treatment, and metallurgical mathematical modeling. Currently leading the hydrogen initiative in Tata Steel. Published more than 60 technical papers in peer-reviewed international reviewed journals, has 8 patents, and co-guided 3 PhD scholars.
Sharing
And his
it.
topic is reduction in GHG emission in the context of steel industry.
Thank you. Thank you for this introduction. I hope I am audible.
You're audible. So
Thanks.
let me share your presentation.
Yes, please.
Yeah. So it's here, sir.
Yeah, thank you. Thank you for sharing, and thank you organizers for giving me this opportunity. In my discussion or in my talk today, I'll cover mostly the requirement of hydrogen in steel industry, where it is required, how much it is required, and why this is required. And I think that will give enough data points for arranging or strategizing the transportation of hydrogen in future. Next slide, please. And is it possible to make it full screen?
Okay.
Okay. India is emitting around 2.65 gigaton of CO2 per year, and we come actually in the third in the world in terms of emission. And if we move to the next slide, we will see that 8.5% of this actually comes from the steel industry. So the use, the decarbonization of steel industry is of course essential, and this is what we'll deal with today. Next slide, please. And next slide. Next slide again. Yeah. So, the IPCC has given us the 3 representative concentration pathways. We all know that the temperature of the Earth is increasing, and the most acceptable pathway is the RCP 2.6, which talks about increasing temperature by 2 degrees. And this is where we must content the temperature of the Earth in order to save the mankind. So how to do this? There is a methodology which is described in the next slide, please, where the carbon dioxide concentration in the atmosphere must be limited to a level of 450 ppm. Right now, it is about 415 ppm, and we have only about 35 ppm, in our hands. In order to achieve that 450 ppm target, we need to come to a net zero scenario in the world by 2050. And if we talk about net zero scenario in the world, of course, we are talking also about the net zero scenario in the steel industry. And let us see that what are the challenges and how we could achieve this. Next slide, please. So this is who are discussing here the regional steel production projection. And if you see here, the challenge that we have, the bit here, the middle bit here, the yellow, the steel production in India is going to grow, whereas the steel production in the rest of the world are going to be at the same level. In Europe or even in China, it is going to decrease. So even if we have technologies to reduce the CO2 emission per ton of crude steel, the total emission is going to increase because of the fact that our steel production is going to increase from about 120 million tons to 400 million tons by mid-century. So that is why the challenge for India is most difficult to achieve this net zero target. Next slide, please. Yeah. So here, what we tried to show that how big is the problem really, how huge is the problem. So in order to produce 1 million ton of crude steel, we use about 0.34 million ton of coke, about 0.22 million ton of coal. And when we produce 1 million ton of crude steel, we produce 2.5 million ton of CO2. And how big is 1 million ton of CO2? So, 1 million ton of CO2 is enough to fill up 225,000 Olympic-sized swimming pools. Or in order to, get it absorbed through different plants, we would require 2,750 square kilometer of forest. So that is how huge it is for 1 million ton of CO2. And you can imagine if our production reaches 4 million ton, and at a rate of 2.5 million ton of CO2 per million ton of crude steel, then how big that problem would be in future. Next slide, please. Yeah, this is where we just quickly show the value chain or the process chain in the steel industry. It starts with different ore and coke mixture, which is fed into a furnace called blast furnace, where we make molten iron. Molten iron has very high amount of carbon, so it cannot be used as steel. So this is transferred to a different furnace called basic oxygen furnace, where oxygen is blown and the carbon is oxidized, and that is how we make steel. And then, of course, the steel is shaped or rolled in different forms. Go to the next slide, please. Here we are showing that at different production processes, at different production stations, if I may call it, what is the emission? You can see here that the 70% of the total CO2 emission come from somewhere called blast furnace. So blast furnace is somewhere where we make the iron, not the steel. And this is where our concentration would be in order to decarbonize quickly. Next slide, please. And of course, there are other ways of making iron, that is DRI technology, which is there available commercially. And here the coke is not used for making iron, but natural gas is used. And the carbon dioxide emission is also less, about 1.4 ton of CO2 per ton of crude steel. But there is a problem because this process requires natural gas. India is not having its own big reserve of natural gas. Also, the natural gas cost in India is quite high. It is about $11 to $12 per MMBTU. So it is not really something that will give the steel industry any profit after making the steel. And overnight changing from blast furnace technology to DRI technology would also not be feasible because of the capital investment. Next slide, please. So what is the way? How can blast furnace be decarbonized? The one way, of course, there is efficiencies which can be improved and should be improved in order to decrease the CO2 emission. But another way is to inject hydrogen-bearing gases into blast furnace. Hydrogen-bearing gases means it could be syngas, it could be hydrogen as well. That will reduce the specific emission by 0.2 tons per ton of crude steel. So that means it reduces, but it doesn't bring us to the net zero. And in the short term, if you go to the next slide, please, in the short term, this is one of the methods that we must take, along with the fact that we have to use more scrap in the steel, we have to use more and more DRI in place of blast furnaces. But all of this would not help us in coming to a net zero scenario. So what is the net zero scenario and how we can achieve? Let us go to the next slide and discuss. There are two major challenges here. The first challenge, of course, the production of economically viable green hydrogen. And second is development of technologies for carbon capture and use and sequestration. Now, before we go to the next part, let me describe why is hydrogen used, why hydrogen is told to be a good avenue to get the decarbonized or decarbonizing the steel. It is not about energy. It is also about its power to reduce oxides. Hydrogen is a much better reducing agent than any of the carbon-based reducing agents. That's why hydrogen is so popular, and it has to be used in a manner that we can make sure that we reduce the use of coke and bring the total emission to zero. Next slide, please. In Tata Steel, we have taken a three-pronged approach in order to tackle this problem. The first one is direct carbon avoidance, where we would be replacing the polluting blast furnaces with different technologies, as I described, and we will be using hydrogen as a fuel. The second would be the carbon capture and utilization. Why not sequestration? Is because the geography of India is not good enough to go for any sequestration of CO2. But utilization would be possible. And in utilization also, we would require hydrogen in order to make hydrocarbons from the captured CO2. Tata Steel have already piloted the capture technology here in Jamshedpur. And we are also going to make a pilot plant in order to convert it into different alcohols. But you can see in both cases, for CCU or for carbon direct avoidance, we require green hydrogen. So that would be the center point of research, of technology development for next few decades. Next slide, please. So quickly, this slide actually describes in the x-axis the volume of hydrogen that can be used in a technology, and y-axis the ton of CO2 emitted per ton of crude steel produced. So in the left-hand side upper corner, you can see there are common technologies for iron making, and those cannot take a lot of hydrogen into the system. As a result, the emission will always be high. But the DRI technology, which is supplied by Midrex or HOLZR, those are technologies where already 50 to 60% of hydrogen is taken as input. And they are developing their technologies further in order to have 100% hydrogen as reducing agents. And when you do that, then the total emission of carbon will come down to zero. So that is the most popular and most probable pathway to come to the net zero. If we move to the next slide, we'll see that in Europe, there are already, I think hybrid mention was already there during the introduction of this seminar. And there are other programs like Salcos, there are programs which has been taken by ArcelorMittal and POSCO, where hydrogen is going to be used to produce steel in place of coke. And those will be used in different form of DRIs. Next slide, please. Yeah, so let us now talk a little bit about the numbers, because that will be interesting and that will be also a guiding principle for the transportation in future. So currently, if we use DRI technique to make iron or steel, then we would require about 10.9 million MMBTU of natural gas to produce 1 million ton of crude steel. And that will emit about 1.56 million ton of CO2. However, if we change this natural gas with hydrogen, which is correctly pointed out in the right, we would require 65,000, roughly 64,000 tons of hydrogen to produce 1 million ton of crude steel. And that will bring the emission to almost zero, as has been pointed out here. But then, of course, you have to multiply this number with the amount that you have to produce as a country in terms of the growth in the steel sector that we have already discussed. Next slide, please. Next slide, please. I'll not go into detail, but I must mention two things here. One good thing about hydrogen in steel industry is that we don't need very pure hydrogen. We actually need about 80% pure hydrogen. Of course, it should not have, sulfur in it. It should not have a lot of CO2 in it. But let us say that we have a mixture of some amount of 80% hydrogen with some amount of CO and some amount of nitrogen. It will be a good idea to use this in blast furnaces, also in the DRI. So we are not really planning for something which is very pure. I'll not go to the Tata Steel specific plans, but the cost that we are aiming for is actually less than $1. I'll not be able to show the detailed analysis, but $1 is something which will be the break-even point for future. And the CO2 footprint, of course, has to be as low as possible. Currently, we're discussing about co-creating or co-locating those hydrogen units with the steel plant. But even after that, the transportation will be important, because there will be a lot of hydrogen which needs to be transported from one place to the other. And that is why transportation and the steel development for transporting such a gas would be important. Next slide, please.
Mr. Kundu, sorry for interruption. Kindly expedite and please finish it in 2 to 3 minutes.
Right. Okay. Thanks. So I'll just talk about the three different generation technology that we are working on. One is the CLC system, which we are working with an American partner. The biomass gasification is something that we want to emphasize a lot, and the biomass gasification is something that we want to carry on in future. Why? Because if biomass is used for hydrogen production, then what will happen in the source itself? You reduce CO2 emission, not by using, but just by producing CO2. Of course, electrolyzer, you all know, it's popular technology, it's already established technology, but only one problem there, that it has got a big capital footprint. So its capital expenditure is high. Next slide, please. Quickly, what is the resource required? For electricity requirement for electrolyzers, for 1 million ton of hydrogen, we require 52 gigawatt hour of electricity. For biomass route, for 1 million ton of hydrogen, we would require 13 million ton of biomass. So this has to be streamlined. The resources are there available in India, but we have to streamline the supply chain. Next slide, please. Next slide. This is almost the penultimate slide of my talk. So in the CCU, that means carbon capture and utilization, we have tried to formulate that which one is the best one to produce, because here you're talking about developing a product which needs to be sold. So what we are finding right now, the alcohol and the methanol or ethanol are the two products which would be the future to be given emphasis on. So this is what we are trying to do in Tata Steel as well. Next slide, please. I'll not go to the concluding remarks. In the next slide, I've just acknowledged few of my team members. If moderator could show that. Next slide. Yeah, these are the team that is working in Tata Steel who are working with me. Thank you very much.
Thank you, Mr. Kundu. A very informative presentation on usage of hydrogen in iron making, motor metal making. This is surely a future for the country like ours. Thank you very much.
Thank you.
So next speaker is Mr.Atul Srivastava, Vice President of Quality and Technical Services in Welspun Corporation Limited. He has vast knowledge on steel with 30+ years in experience in chain steel manufacturing, achieved several milestones such as qualification of service pipelines, developing steel for critical applications like defense, nuclear, and construction. Currently, he is leading the development of pipeline for hydrogen and CO2 application. He is actively participating in key research programs happening worldwide. The topic for today, Mr. Srivastava is covering future infrastructure readiness for transportation of hydrogen gas through pipelines. So, Mr. Jsaw, I'm just sharing your presentation.
Thank you, sir. Thank you.
Yeah, this is it.
Yes, sir. To the full screen, please, sir. Yeah.
But it is a PDF, so it is already full
Okay,
screen.
no problem, sir. No problems. Anyway, good morning and good afternoon, ladies and gentlemen who are there in the conference. It's a pleasure talking to you all through this digital webinar platform. I'll be talking more onto the future infrastructure readiness for transportation of hydrogen gas pipe through pipelines. You must have seen the earlier presentations where the pipeline seems to be the most economical and the most reliable, because everything is related to the cost. Next slide, sir. This is my presentation sequence. I'll briefly speak about Welspun, then the critical requirement for line pipe steel making. Then I'll be talking about something about hydrogen transmission and distribution pipelines. Then a brief on CO2 pipeline and the way forward. Next slide, sir. Welspun is top 3 among the line pipe manufacturers globally. 50+ approvals from oil and gas major qualifies for global bidding. 15+ million metric ton of pipelines already delivered. Next slide, sir. I'll just run through this. We have different products: the Jsaw pipes, the LSAW pipes, the RW pipes. We are coming up with the DI pipes in coming couple of months. Next. As it has become a necessity now rather than a choice, that we have to go through this journey of environment, social, and governance. So Welspun, as a very responsible organization, is also going through this journey where we have planned for various environmental and social and corporate governance framework. Next slide, sir. The sustainability targets what Welspun Corp has taken is net carbon neutral by 2040, water neutral by 2040, waste to landfill, zero waste to landfill by 2040, and subsequent, the parameters what is it's a target which we are aggressively working, and that is something which is, again, I'll say that it is not a choice now, it's a necessity. So next slide, sir. Then I'll run through some critical parameters which is required to develop steel for 100% hydrogen transportation, and this is based on the current specification, current data is available, and as we are aware that a lot of research is going on and across the globe to develop line pipe which is in compliance with the industry requirement. But fundamentally it has to be the chemistry design should be with low carbon, a very highly optimized carbon equivalent and PCM, optimized titanium by nitrogen ratio. It should be, the steel should be as clean as possible with minimum of segregation, and with heavy reduction at low temperature and uniform fast cooling. That is the essence of TMCP rolling, which most of the mills in the world can do it right now. So next slide, please, sir. This is a typical flow chart of steel making. Blast furnace. Dr. Saurabh Kundu talked a lot about blast furnace. So that is meant for liquid metal. Then you have the desulfurization unit. Then obviously you have to remove the phosphorus, take it through LF for the chemistry control, then go for a degassing and calcium treatment to make steel absolute clean. Try to go for a vertical caster, which will minimize the inclusion into the casting. Many of the mills have curved caster, but still with the soft reduction and some other features, they can still control the requirement. So the next slide, please. The TMCP rolling, this is what is going to be very important. I'll not go into the details of this, but this is from one of our very esteemed steel supplier. What is very critically required for steel to qualify for 100% hydrogen transportation is going to be the fine grain structure, preferably 5 micron, microstructure of more of ferrite and benite, preferably granular benite or acicular ferrite, without any trace of perlite. Perlite will be very harmful for transportation. The hardness has to be restricted to 220 HV10 for the base, and 235 HV10 for the line pipe, including the weld and HZ. So next slide, sir. This is the control of macro segregation. As I said, people do prefer vertical casters, but yes, all the mills cannot have it, do not have it. They should have the soft reduction, minimize the segregation level to the, we are talking of 1 or 0, something like that, which is going to be critical for the hydrogen transportation. Next slide, sir. It is a sum up, an absolute clean steel. The numbers are given for the sulfur, phosphorus, triumph elements, control of centerline segregation. That is very, very important. And alloy design for resistance to hydrogen abridgment should be such that the carbon is low, with a combination of chrome, nickel, moly, niobium for a grade something like X70. So next slide, sir. That's a typical cross section of the weld joint. We have to have the weld as well as the HZ in control, so that the failure does not happen from these critical areas. So next, hydrogen pipelines. There are almost 359 projects already announced in the globe, with an investment of almost $500 billion. So next slide. This, it's nothing new. My esteemed colleagues have already spoken about it. The brown hydrogen, the blue hydrogen, and the green hydrogen. So next slide, sir. Hydrogen pipeline. There are almost 1,600 miles of pipelines already existing in United States, which is operating with hydrogen. Europe has obviously taken up several projects to transport hydrogen through pipelines. My other speakers have already spoken about it. The critical challenges what we see, or what needs to be catered while designing the proper steel for use of hydrogen pipelines, and obviously the lot of research is happening, is the potential for hydrogen to embrittle the steel wells used to fabricate the pipelines, the need to control hydrogen permeation and leaks, the need for lower cost, more reliable and more durable hydrogen compression technology. That is to increase the pressure so that the larger volumes can be transported into the lesser diameter pipes. One possibility for rapidly expanding the hydrogen delivery infrastructure is to adapt part of the natural gas delivery infrastructure to accommodate hydrogen. That is what repurpose of the existing hydrogen pipelines are being talked about. It can be 10%, it can be 15%, it can be 20%. It's again case-to-case basis. There's no standard thumb rule available at the moment. That is immediate. It can be started, and subsequently it can be shifted to 100% hydrogen with new infrastructure. Or in fact, we can look at it in this way, that whatever new pipelines are designed, they are compliant to the hydrogen requirement 100%, so that in future, if it's to be converted, it can be converted. Next slide, sir. This is a hydrogen pipeline. Typical hydrogen pipeline requirement will be from LSAW or HFW. The grades will be from X52 to X70. The diameters typically, these are the estimated numbers. There's no hard and fast rule for that, 4-inch to 24-inch. The thickness what we are talking of today is 6 to 24.6 millimeter. It can be higher with subsequent inputs coming in. The present standard which is being referred to is the ASTM B31.12. Feasible types of hydrogen pipeline: construction of a new hydrogen pipeline, blending hydrogen, repurposing of the existing natural gas pipelines. So these are the three options available with us. Hydrogen pipelines over electricity lines. Hydrogen pipelines are cheaper than electricity transmission lines. This statement when we are making is compared to, if you generate hydrogen at one location and transport it with the pipeline, or you generate electricity and generate hydrogen at the second location. So, and that's the thought process. Hydrogen pipelines can effectively transport renewable energy. Using renewable energy for long distance, they can transport 10 times the energy at the 1/8 the cost. And Mr. Chaudhary has already given details about in the previous slides. So to the next slide, sir. Hydrogen transmission and distribution pipelines. Again, it's a comparison between onshore transmission pipelines, subsea transmission pipelines, distribution pipelines. These are the numbers. Of course, these are already available in the public domain. So I'll not spend much time on this, because this is something which is evolving continuously with more and more research and data coming in. So next slide. This is again a distribution, transmission, a comparison, pipeline, shipping, and trucking. If you see, it is more effective to use pipelines for whether it is retrofitted or new. It still works good for a good distance of transportation. Next slide, sir. The key consideration for a new or repurposed hydrogen pipelines per se, as a pipe manufacturer, if we look into it, we have highlighted that rest of the systems come with the operation and maintenance people. The brittle fracture mechanism in steel lines, which is already existing, toughness and tensile strength parameters of the existing pipelines. When we go for a new pipeline, obviously the material selection of steel, or whether it can be steel, plastics, or composites. And when it's a long cross-country pipeline, obviously steel, then you have to go into the specifics of steels, and obviously the correct welding and jointing issues. That is something as compared to the new pipeline. So next slide, sir. A brief on the CO2 pipelines. There is an existing DNV recommended practice which was concluded last year, and it is already available now for the use. And of course, ASME B31.4 talks about it. DNV F101 also talks about it, and obviously 5L is there.
The typical requirement which is coming in is thickness of 5.2 to 27 mm thick. Diameter is from 152 millimeter to 1219. And the pressure what is being talked about is 21 bar to 200 bar. These are again based on the projects which are either under advanced feed or are being under design now. So next slide. The key consideration for new and repurposed CO2 pipelines. Again, I'll talk about the highlighted part of it: impurities in the CO2 changing fraction propagation, and fatigue and cycling effects of the repurposed pipelines. And for the new, obviously, the selection of the line pipe per se, considering the existing specifications which is already available. It is not like CO2 has been, there is a lot of research being done. So obviously the specifications are available. So it's much easier as compared to hydrogen. And hydrogen will evolve in next 1.5 years, 2 years time. We'll have a lot of information available, and all the concerns related to safety and criticality will be addressed. Next slide, sir.
Mr.Atul, please expedite. Sorry for
Sir, this is the last slide. This is the last slide, sir. Welspun has been working with national and international steel manufacturers for developing clean steel. Welspun has decades of experience in manufacturing pipes for various critical applications like onshore, offshore, and transportation of critical gases. We strongly recommend the usage of carbon steel pipelines for transportation of hydrogen, tuning the requirement of critical parameters. As per understanding, several projects worldwide are under execution using carbon steel pipelines. Welspun would like to be part of supplies for these project owners, domestic or international. Next, sir. That's all. Thank you very much. Thank you for the time. Thank you for the time.
Thank you, Mr. Srivastava, for your very elaborative and informative presentation. Thank you very much. So next speaker is Mr. Kamal Kishore. He's a chartered engineer from Institution of Engineers, life member of Institute of Metals India, member of Institute of Engineers India. Over 20 plus years of experience in manufacturing saw edge, stainless steel, flat pipes, hot and external bands, and connector casing. Also experienced in fabrication of heat exchanger, pressure vessel, plant piping, and layout of cross-country pipelines. Worked for the companies like L&T, Welspun, Sabic, Saudi Arabia, Arabian Pipe Mill, and has published many papers in international journals. So, Mr. Kamal, I'm just sharing your presentation.
Good afternoon, everyone. Can you hear me?
Yes, you are audible. Yes, and your presentation is okay?
Yeah.
Continue, please.
Good afternoon, everyone, and thank you, ITA, Dr. Chandel, Mr. Kathayat, and the team for giving me the opportunity for presenting the webinar. Actually, my previous colleagues who have presented the requirements of hydrogen is even in India is more than 5 to 6 million ton, and other colleagues have spoken about the steels and blast furnace. So my talk will be based on the how to transmit this hydrogen to the either a steel plant or a processing unit. So I will be talking about the clad pipes, which can be used as a hydrogen gas transmission. Next slide, please. Okay, just to have a brief about hydrogen. Actually, hydrogen is having a lowest, this is the first element in the periodic table and is the lightest one. And hydrogen can be used, as all has said already, hydrogen can be used as an alternative to the fossil fuel. And if we burn it, it will give you the hydrogen. Hydrogen will give you the water. It will not give you the CO2, and it can be a cost and environmental friendly solution. Next, please. Okay, as we know, the pipelines are the the blood vessels, you can say, of the any country in which we are transporting like gas, crude oil, or any other like water also. But here we are talking about the hydrogen pipeline, because pipelines are the safest mode of transportation, more reliable and less hazardous, and we can transport the gas at the lower transportation cost. But there are many challenges to transport the hydrogen, like we need a steel which is a sulfur and phosphorus control, because if the steel is not capable to handle like hydrogen assisted fatigue cracking, and it may have the hydrogen embrittlement, there will be the strength and toughness loss due to the hydrogen embrittlement. So hydrogen can be affect this surface or even subsurface. It can have, if it is in molecular and it is dissociate with like Sievert's law, the ionic hydrogen can trap into the pore. It can go to the high stress area and can increase the brittleness. The next slide, please. So what is the challenge? Actually, now available standard is ASME B31.2, which is considered the safety and the challenges of the hydrogen. So what actually hydrogen pipeline demands is, if the structure must be free of any detrimental effect, which is having a detrimental effect. The sulfur must be controlled less than 10 ppm, and if we weld it, it requires a uniform microstructure that may need the PWST, post-weld heat treatment, and also it demands the good toughness. Next, please. Next slide, please. Okay, which kind of steel we can use in the hydrogen gas pipelines? We can use the carbon manganese steel, which is not only used in API pipelines. We can use stainless steel. We can use the clad steel. We can use plastics and composites. But there are certain limitations of using carbon and manganese steel and the plastics, which may have a embrittlement. So best solution is to use a stainless steel, especially 316 grade of stainless steel. Next, please. Next slide. So we are talking about the corrosion resistance alloy, which can be used for hydrogen gas transmission versus clad product. If we use a pipe of complete with CRA, or if we use a cladded pipe with CRA plus a Becker steel, means the carbon steel, that can be the carbon steel, we can have a cost benefit and the weight benefit. Next slide, please. That can be discussed in next slide. Say for an example, if we use only CRA, which is say SS316, of if suppose there is a line of 24 inch having a maximum allowable operating temperature of 10 MPa, so we require a thickness of 18.86 mm, while if it is a API X60M grade steel, we require the 7 mm of thickness, 7.7 mm, and then you can see the weight difference is a huge. If we use this carbon steel along with the CRA layer of 3 millimeter, the gross weight will come around 1.9 metric ton. So there is a difference of around 54% by weight, you can see. So definitely this is a huge saving which can be considered during the decision of the material which can be used. Next slide, please. So cladding advantage, we have already know that it's a corrosion resistive material is inside the carbon steel, or it's a very economical because there is a less weight we can use during construction. Next slide, please. So what is the material can be used? As I said, the stainless steel can be used like CRA, titanium alloys, nickel alloys, copper we can use, zirconium we can use, and the backer base material can be the carbon steel or alloy steel. So normally the CRA layer would be 2 to 4 millimeter depending upon the design of the pipeline. Next, please. So there are few processes of producing the clad pipes. One is metallurgical bonding process, another is the mechanical bonding process. Metallurgical bonding is fusing both the material CRA and the backer, it means carbon steel. So there is 3 category. One is roll bonding we can do by explosion bonding, or we can do weld overlay. And the next category is mechanical bonding, where there is no fusion between the CRA layer and the carbon steel. That is mechanically lined. So these are the 2 main processes we can use. Next, please. So as I discussed that the plate can be used to form the large diameter pipes. That is what is the plate we can use. There is a backer we call that can be a carbon steel or low alloy steel, and there will be a clad, the backing steel will be cladded with the CRA, corrosion resistant steel. So next, please. So I will discuss about the roll bonding process. So as we already listened about the steel making, so there will be 2 material. One is cladding material, another will be the base metal of carbon steel that is joined and sealed together and then rolled. After rolling, it is splitting in 2 parts, and after cleaning and cutting, that can be used for the pipe making. So this is the one process which comes under the metallurgical bonded plates. Next, please. So another process is explosion bonding. In this, the already produced plates like carbon steel and alloy steel can be assembled like this, and the backer means carbon steel will be at bottom side, and then CRA will be placed over the backing steel, and then TNT is used to blast the blasting this explosion. Once this explosion is completed, then the plate is flattened and tested and is uniformly cut to use for the further processing. Next. Okay. Next process is we can use the weld overlay process to produce the cladded pipes. The process can be used electroslag, strip cladding, sub-arc, flux core, GMAW, tungsten, and SMAW. There are some limitations over these weld overlay processes. Next, please. So the problem with the weld overlay is we have to deposit more to get the lowest dilution. If we deposit less, then dilution from the base metal will be more. So we will not get the accurate chemistry on the surface of the CRA. So this is not this is a costly process, we can say, and have some other problems with this. The base metal is heated and the properties of the backer can be altered. So it's very much care has to be taken during the weld overlay process. So next slide, please. So as I discussed about the problem with weld overlay, there will be loss of strength and toughness. The residual stress will be developed during the welding. Distortion will be there. The consumable cost will be high because we have to deposit more material to get the desired chemistry. Next slide, please.
Mr. Kamal, please complete it in 2-3 minutes.
Yes, sir. I will definitely try to finish it in few minutes. I will discuss about the clad manufacturing which we have undertaken at our Jindal Saw facility. So the pipe is produced by JCO process. You can see this electroslag welding process under process. Next slide, please. So we have produced the pipe from a JCO route, which is everybody aware about the process. I hope. The next slide, please. So we have taken the base material as a X60M of 15 millimeter, and the cladding layer was 316L of 3 millimeter. So chemistry can be seen here, the 316 and X60M. Next slide, please. So there is a very much important for the welding and joint preparation. This is very crucial for the clad pipe. If we are not doing the proper joint preparation, we will be end up with the many defects and cracking. So we have to remove the CRA like this. You can see in the picture 1. So after removing and preparing the bevel of the plate like this, like picture 1, and then we have to process the tacking here at the OD, and then we sub arc at ID and OD, and completing the joint. The clad weld, which is done by electroslag welding, can be completed to restore the CRA layer. Next slide, please. So we have used normal carbon steel consumable, which are widely used in pipe mills like ER70X6, and titanium boron wire, and the strip that is 316L. Next slide, please. The chemical composition of flux. The flux is for sub-arc welding, we have used aluminate basic, but for the electroslag welding, the CaF2, calcium fluoride basic flux is used. Next. So these are the parameters which we have used during the sub-arc welding. We have used 2-wire technology only. And for the cladding, we have used electroslag strip process. The speed is lesser in the strip cladding. This is the limitation here. So next slide, please. So we have achieved the chemistry of CRA layer, which is nickel, which required like as per API 5LD. There is a specification for clad pipe manufacturing. The nickel requirement is 10 to 15, so we achieved 11, and the chromium is achieved 17.51, and mol is 2.41. So that is within the standard requirement. Next slide, please. Next. So this is the macro of the clad plate. We can see the CRA layer and the backing plate. CRA is consisting of austenitic phase. Next, please. So this is a macro of the complete weld joint, including the electroslag layer. It's a complete. You can see the complete joint penetration and complete fusion. Next slide, please. So you can see here there is a difference. You can see the weld microstructure before weld cladding. So there are many. You can see the Wiedemann-Staten ferrite and polygonal ferrite. You can see, but if you perform the electroslag welding, this weld is get refined and you get the very fine microstructure. So mechanical properties, the tensile, we have conducted the tensile which met the required properties. Next. The toughness, toughness, we have conducted base metal, fusion line and weld metal toughness before and after the electroslag process. So here there is a difference. Here in weld metal we could able to achieve the 182 joule at -20, but after completion of electroslag, it slightly improved because our microstructure is get refined from the electroslag process. So this is the reason here. The hardness is a issue here. You can see the hydrogen, this hardness before this electroslag was around 208, but after this electroslag strip cladding, slightly it is increased. This is increased because of we have used the titanium boron wire, and which is having the tendency, if we reheat the titanium boron weld metal, it get higher hardness. So that can be used, means other wires can be used if we want to reduce the hardness, but still this is well below the requirement of the standard. Next slide, please. So yes, there are very much important test, that is shear bond test. Shear bond, we have to conduct the shear bond test between CRA and the base metal. So we conducted the shear bond test and found that it is well within the standard range. Next. We conducted the corrosion test also as per ASTM practice E, where we have used copper sulfate and sulfuric acid solution, and we have boiled it at certain temperature at 15 hours, and after completion of that we band it and found there is no cracks. So conclusion, so we can manufacture the clad pipes with getting the pre-cladded plates, and that will definitely work in a highly corrosive environment and hydrogen gas transmission. Our properties were well within the range, and that's it. Next. Thank you very much for the opportunity.
Thank you, Mr. Kamal, for your informative presentation. Thank you very much. Now we are at the end of the session. Now the next session is question and answer session. So most of the question has been answered during the presentation by the presenters. The question we have received. So, Ganesh sir, do you want to answer some question or move to next session?
No, I don't. I think you have the questions. You people can take this question.
Yeah, I've seen these questions. These questions are already answered during the presentation.
Yeah, you can ask the open people, participant, if they have questions, they can post into the question answer sessions, and you can represent to the different speakers and experts. Take these questions if there are any.
We can do that. So, last but not the least, I request Mr. Yogesh K. Bhatia, please, for the vote of thanks for this presentation. Mr. Bhatia, please.
Jaidev ji.
Good afternoon, everybody. And it's a pleasure to present a vote of thanks to the very learned speakers who have really given us a good information about this future fuel requirement of the world, which is hydrogen, green hydrogen, and then how to take it up to the end user through the pipeline. And before I tell something about what the speakers have mentioned, I would like to mention that for all of us, that the Düsseldorf trade show is being opened up, and now the German authorities, they have cleared that from September the shows can take place. So the Düsseldorf Tube Show has already been planned and the dates have been announced, which are from 9th to 13th May 2022. So I would like all the participants to note that down, and we look forward to seeing all of you there also. As usual, the Indian contingents are very large and Indian participation by the industry is also huge. So I hope that this time also it will be the same way. And I also would like to thank the International Association, Mr. Düsseldorf, who helped the Indian chapter to conduct the seminar. I think this is the second or third webinar which we have conducted during this pandemic conditions. So, and I am sure that we will continue doing the same, these kind of seminars, webinars, because we find that the participation is also very good. We found that about nearly 350 participants had registered, and about 150 people have participated. And right now, even at this stage, I find nearly 120 people are still present, who have listened through all the presentation. So as we have already crossed our time limit, I would not like to take any more time. And Mr. Jayachandran, Mr. Chandel, I think you can take it through for the closing.
Okay, sir. Thank you, sir. Thank you very much.
Yeah.
And
Yeah.
as Mr. Bhatia mentioned, I again mentioned that the Messe Düsseldorf is organizing a tube Düsseldorf, which is planned in 9 to 13 May 2022. And Indian chapter is organizing Tube India, which is planned in 23 to 25 November 2022. So thank you again for participating, and the speakers who presented the presentation on various topics to share the information, share their research to the participant. Thank you very much.
Thank you all. Thank you very much. Thank you.
Thank you.
Thank you, sir. Thank you very much.
Everyone.